What we want to talk about next is Newton's method. And Newton's method is a way to use calculus to find approximate roots of equations or solutions. Approximate roots meaning the solutions for equations. For example, this little equation here, 0.5 x to the fourth minus x cubed minus 1 equals 0. Now that's a nasty equation for a lot of reasons. One thing, I got a half. Another thing, I've got x to the fourth, x cubed, but I don't have x squared or x. Yeah, that one's going to be, and it turns out the roots are not even whole numbers or integers either. I don't believe any of them are. So for a lot of reasons, the solutions to this, or the roots, difficult to find. Well, Newton's method is one way we can find these, and a lot of calculators actually too use this sort of algorithm as well. But anyway, here's how it works. If I take a look at, and this could be any equation, I think this one might sort of resemble that one. But anyway, part of the graph looks like this. Something like that. So this is my y equals f of x, which, you know, in this case the f of x is just the side that doesn't equal 0. All right, so I graph that. Okay, well, what am I talking about on the graph over here? If this graph, if I'm graphing that, the solutions to this equals 0, isn't that where it crosses the x-axis? The real roots are? Yeah, so I'm talking about the root here, r, being that x-intercept. So that's one of the key ingredients here. To know what we're talking about, if I'm finding the roots of an equation that equals 0, an equation that has equals 0 in it, if this side is, call that my function side, then the root is the x-intercept, the real root. Well, how do we go about using calculus, or what is Newton's method all about? Well, Newton's method does this. Newton's method says, well, let's guess at it. I mean, it's probably, you know, whatever it is, irrational. It's probably an irrational number. So let's take a guess at it. Let's say that a nice number close to that is this x, call it x, x1. I'm going to go out. Probably wouldn't go that far out, but just to make it where I can draw my little picture. Here's what Newton's method does. It says, well, let's take a guess, x1. That's our guess. Well, obviously x1 is not the answer. And so what I want to do is get a better estimate. And the way I get a better estimate is this. If I take a look at then the tangent line for x1, okay, tangent line of x1, I've got that. Okay? All right, so let's talk about that tangent line at x1. Well, for a line, you need well, let's just think about it. All right, so here it is. So this point here would be x1, comma f of x1, right? So the tangent line would be y minus y1, using the point slope here, equals m times x minus x1. Okay, and so that would be, what's my m? What's my slope of that tangent line? It's a derivative, right? The slope is the derivative. So the derivative of x1 would be f prime of x1 times x minus x1. Okay. Well, here's what I want to, so that's my tangent line. Here's what I want to do with that, though. Do you see here a better estimate shows up if I find that tangent line? If I find that tangent line here and I go to this x-intercept for my tangent line, that's a better estimate. You see that? Because I went from x1, and so if I find this x-intercept of that tangent line, call it x2, that's a better estimate. Well, look at this. If I use, so this point on this tangent line would be, since it's an x-intercept, that would be x2, comma 0. Well, let's just put that in here, and I'll show you why. So if I put that point in to this tangent line formula, the y is 0, and the x is x2. Why do I do that? Well, the goal is to find this estimate. So let's solve this for x2 here. Solve this equation for x2. Of course, that goes away. So if I solve that for x2, and the way I'm going to do it is, let's divide by f prime of x1. So I have minus f of x1 divided by f prime of x1 equals x2 minus x1. So I add the x1 to both sides. And so let's set it up like this. And so here's what that gives me. What this formula gives me, notice the x2 is in terms of everything x1. So here's the thing. If I plug in, if I want this better estimate, I just take what my first guess was, plug it into the function, and evaluate it for that function, and then divide that by the derivative evaluated of that function. That gives me this better estimate. Okay? With me. So x2 is my better estimate, and I can find it just in terms of, so that's going to be a better estimate of root r, right, because it's closer than x1 was. So that gives me, just in using these x1, the x1 guess, I can get a better guess using this formula here. All right, well, how do I get better? Well, let's do the same thing for x2. Since x2 was pretty good, what if I do the tangent line at x2 and find x3? Wouldn't that get closer in? Well, guess what x3 equals? A better estimate yet. x3 is going to be the same thing, but using x2's number. So x3 is going to be x2 minus f of x2 over f prime of x2. See that? If I did the very same thing except using the x2's and x3's up here instead of x1's and x2's, I'll get this. Okay? Well, hopefully you get the idea here. x4 is going to be the same thing, but plug in the x3. So we just keep getting a better and better estimate of this root. So x3 is going to be closer to my actual root value. Well, this little formula here is basically is Newton's method. In general, here's what it looks like. If x sub n is the nth approximation of your root r, then x sub n plus 1, the next approximation for your root, is this. X sub n plus 1 equals, we're just going to take the nth approximation minus the f of the nth approximation divided by the derivative evaluated at the nth approximation. That's Newton's method. For finding roots of equations. It just says, well, guess at it, then find this next one here. Then take that, whatever you get for that, and plug it in here again, get the next one. Then take that. So it's just a kind of a repetitious process. All right. So let's actually do one here. Use Newton's method to find the third approximation, x3, so this is the formula you need to remember right there. All right, so use Newton's method. And we'll do this one, do a couple by hand, then I'll show you how you can do it nicely on the calculator. All right, use Newton's method to find the third approximation of the root in 1, 2, the interval 1, 2, for x cubed minus 3x plus 1 equals 0, starting with x1 equals 2. All right, so the graph, just take a look if you want to, just kind of see what we're doing. All right, so we've got this graph here, x cubed, y equals x cubed minus 3x. Plus 1. All right, so we've got several roots here. But what I'm interested in is this root that's in here, from 1 to 2. That's what we're talking about. So it's right there. And so what we're saying is, yeah, let's just guess that it's pretty close to 2. So let's just take our first guess to be 2. So just kind of specified it for us this time. With me? So that's our first guess. The first guess at this root is 2. All right, well, what does Newton's method say? Well, Newton's method said that x2 is you take x1 and then subtract f of x1 over f prime of x1, which in this case works out to be 2 minus f of 2 divided by the derivative at 2. So what is that in this case? Well, this is my f of x, right? So the derivative would be 3x squared minus 3. So f of 2, what would f of 2 be? Plug in 2 there. It'd be 8 minus 6 plus 1. That's 3. And then f prime of 2 would be 3 times 4, be 12 minus 3, be 9. So x2 is going to be 2 minus a third, which is 8/3? No. 2 minus a third. It's 5/3. Had a little brain meltdown there for a second. Okay. Okay? Is that right? 2 minus a third is 5/3. Okay? But that's the second approximation. What's the third approximation? Well, the third approximation would take x2 minus f of x2 divided by f prime of x2, which in this case, that's my x2, so it'll be 5/3 minus f of 5/3 divided by f prime of 5/3. Well, as you can see, you're going to get into decimals and not so nice numbers. By my calculations, saved a little time. This is going to be 5/3. If you do f of 5/3, you get 17/27. Divided by f prime of 5/3 will give you 16/3. You can check me on that, but that's that's what I've got. Which winds up being 5/3. If you simplify this, 5/3 minus 17 over 144, which winds up being 223 over 144. You can check me on that, but that's what I've got. on my notes. I think it's right. But that's not the way we're going to do it anyway. We're not going to have to go through step by step, but you get the idea of what we're doing. Now this is 1.66666 repeating, and this is 1.584611 repeating. Repeat the 1. So it's getting close to 1.5, 1.58, but it's not going to be 1.5. All right. Here's, though, what I'd like for us to figure out how to do. I'd like to get this correct to 6 decimal places. Well, what that's going to mean is I'm going to do this until I have at least 6 decimal places repeating, which I haven't even repeated 1 decimal place yet. So there's a little more work here involved. Here's how I can do that. On the TI 84s, here's what I'm going to do. First of all, I am going to plug in 2. I'm just going to type in the number 2. Hit enter. 2 enter. Okay, well, the next one is, as we know, the next approximation, well, we use Newton's method. We take that 2 and do x sub n minus f. This is what I want to do. Right? Here's how I'm going to enter that in. On the TIs, you should have a little button known as A and S. That takes the previous answer and plugs it in for that spot. Okay, and that's what we're going to use for x sub n. We're going to use A and S for x sub n. All right, so what does that work out to be? It's A and S minus, now what would f of A and S be? Well, that would be, plug in A and S there. So that's going to be, and you're going to need to use parentheses, A and S cubed minus 3 times A and S. I think you just put in 3A and S plus 1. Then I'm going to hit divide by f prime of A and S. So that would be 3 times A and S squared, parentheses, don't forget your parentheses, minus 3. Put that in like that. Hit the 2, hit enter, then put in this right here in the calculator. A and S, which it's on the TIs, it's right there on the negative sign for the TI 84s or 83s anyway. So you do A and S minus parentheses A and S cubed minus 3A and S plus 1 parentheses divide by parentheses 3A and S squared minus 3. And once you get that in, hit enter. You should get 1.66 repeating, what we had for x2. Is that what you get? All right. Now here's the next beautiful thing. That's x2. x3, we need to do the process all over again. Well, there's a couple ways. If you go to if you hit second and then hit the enter button on the TI-84's second entry, that just calls right back up what we had. Now the beauty of it is the previous answer is x2, 1.6. So if I do that again, guess what I get? x3, 1.584861111. Repeating. Okay? So guess what I can do? I can just keep doing that. Now, here's the next beautiful thing. You don't even have to do that second entry thing. If you just hit enter again, it's going to do the entry you just did all over again. So it's going to do that again. So if I hit it again, 1.53239, then if I hit it again, I get x5. 1.5320889. x6 is 1.53. Hey, I'm getting some repeating here. And x7 is 1.5320. Okay, so now everything's repeating. There you go. To 6 decimal places, 1, 2, yeah. I guess you'd round up to 9, but that root is real close to 1.5. Mine's a little off, I guess, but it's 1.532 to 6 decimal places, 1.532089. That's our root to 6 decimal places. How about that? All right. Now, how could I get one of those other roots? How could I get this root? Back on that graph, I started with this one, okay? I just graphed y equals x cubed minus 3x plus 1. And so I found that root's that 1.532 number. How could I get this root? Or that root, for that matter? Just get one of the other ones. There's 3 of them that are showing. How could I get a different one? Start with a different one, right? Here I start with x1 equals 2. So to get a different root, start somewhere else. Where would be a good, if I wanted to find that one, what would be a good one to start with there? Well, let me make a point here. Would it be, let me look here. Would 1 be a good place to start? Why wouldn't 1 be a good place to start for this root? Because remember, this is all based on tangent line. If I do the x equals 1, what kind of tangent line do I have there? Horizontal tangent, and what's wrong with that? I don't get an x-intercept. This is all based on tangent lines and x-intercepts. So if I choose x1 to be 1, there's no x-intercept for that tangent line. So it doesn't cross and give me a better root. So I better choose what, 0? Obviously 0 would be a better choice because it's closer, by my drawing anyway. So let's take up, let's find that other root, x1 equals 0. How do I get x2? Well, using this, right? And the beauty of it, now this is where, you have to put in 0 again. So you go back to your calculation screen there and put in 0. Hit enter. Now I can't do enter again because that'll just give me 0 at bat. So this is where you need to use that second entry. Hit on the TIs at second and then hit the entry button, and it'll cycle through all the things you've entered. But you should eventually get back to this. And once you get back to that, then just hit enter again. 0.33 would be x2. If you have any trouble, just let me know. I'll try to help you. All right, so x3, then we can just start hitting. x3 would be 0.34722 repeating. x4, 0.347296. x5, I want 6 decimal places. x5 is 0.347296. Okay, so there it looks like there's my next root, close to a third. Then we can get the other one similar. Okay? All right, let me do one more. Finish this out. Any questions on that? It's Newton's method. Oh, and the other thing, when I look at these or grade these on the test or homework or whatever, what I'm looking for, I want to see your x1, x2, x3s, x4. So be sure to write those down. You don't have to write down, all the intermediate numbers, just the final answer there. Okay, write those down. All right, so let's do this. Find all the roots for cosine of x equals x squared minus 2x. Using Newton's method, of course. Point number 1. This is different from that other equation. Why? It's not equal to what? I don't have an equal to 0 equation. For Newton's method to work, you need an equal to 0 equation. So what I'm going to do, I want to make it equal to 0 equation. The easiest one, you can do it either way you want to. It doesn't matter. You can move these terms over, move the cosine over. Looks like the cosine will be easier. So let's make this side 0. So it'll be x squared minus 2x minus cosine of x. Yeah. For Newton's method to work, you need an equal to 0 equation. So my f of x for Newton's method is x squared minus 2x minus cosine of x. All right. So next step then, well, I need to know what I want x1 to be. How do I get what I want x1 to be? Graph this thing. Graph that equation. So if I put that equation in, x squared minus 2x minus cosine of x, graph it, I see two roots that I'm going to need to get. One of them looks like it's close to, was halfway between there, and then this one's close to 2, I think. So yeah, I just graphed y equals x squared minus 2x minus cosine. And there I can see which roots I need. And so to get this one over here, well, I can choose wherever I want to. Looks like the best choice would be something like you can use -1/2. I mean, you can get as close as you want to it. I mean, you don't have to use integers or whole numbers. It looks to me like it's close to -1/2. Okay, well, how do I get x2? Well, x2 is x1 minus f of x1 divided by f prime of x1. But to utilize the calculator, I can say a/s minus a/s squared minus 2a/s minus cosine a/s. Then divide that by what? I have to get the derivative. What's the derivative? 2x minus 2. Derivative of cosine is minus sign, so this is plus sign here. Be the derivative. And so x2, the bottom is going to be then 2a/s minus 2 plus sine of a/s. With me? Don't forget parentheses around. So let's put in -0.5, enter, and then put in this, a/s minus a/s parentheses, a/s squared. And once I get this in, then it's easy pickings. 2a/s minus cosine a/s. Now you do have to close the cosine and then close the other parentheses. Divide that by 2a/s parentheses 2a/s minus 2 plus sine of a/s. And that gives me a -0.392965. Blah, blah, blah. All right. I want it to 6 decimal places usually, so how do I get x3? Well, once I get that all in, then just start hitting enter. x3 then will be the next one, -0.3877348. x4 is -0.387722. x5 is -0.387722. So there's the 6 decimal places, that would be, looks like x5. What about the other root? This one right here. Well, start x1 different. x1 there, it looks really close to 2, doesn't it? It looks like it's right on 2. I don't think it is. But so we just start a different place. Go back to your calculate, put in 2, hit enter, then just cycle. You might have to hit second entry a couple times, but you should get back to it. x2 then would be 1.856959. x3 is 1.850729. Dot, dot, dot. x4, 1.850717. Yeah, it's not 2, is it? x5, I get 1.50717 again, so there you go. Negative 0.387722 and 1.850717. That's 2 I get. Is that okay?